Hello everyone, it's Katrina here. Today we're going to be going over questions and answers from the Machine Learning Math Refresher. So on July 2nd, I taught the ML Math Refresher as part of the ML Summer School hosted by CohereLabs. So happy to see so many of you attend the session. It was really great to get to know all of you. But because of time constraints, we didn't really have enough time to go into the Q&A. So I looked at a lot of your questions that you've posted on Discord afterwards and on the Q&A from our previous call, and I just gathered some answers for all of us. And please feel free to comment on this video if you have any further questions, and also be aware that on July 14th, CohereLabs will be hosting another ML math session, and I can go over any questions that you have then as well. So just for a bit of background information, I'll just tell you the agenda that we covered that day so you have a bit of context for what we're going to be looking at today. So during the ML Math Refresher, it was really to build everyone's foundation of mathematics before we dive into the rest of these machine learning sessions. So we started off with derivatives. We covered all the 4 derivative rules: product rule, quotient rule, chain rule, power rule. And then we went into partial derivatives and multivariable calculus. We then showed how partial derivatives are used to calculate gradients, and how gradients are very fundamental in machine learning for calculating or optimizing various different algorithms, especially when we're trying to minimize these cost functions in neural networks, for example. We then switched over and looked at the linear algebra side. We dove into Cartesian vectors, how to do operations between them, and then really dove into our distant metrics, which are so important for large language models and understanding embeddings and relationships in NLP type settings. In particular, we looked at cosine similarity and Euclidean distance. And then finally, to wrap up the session, we started looking at eigenvalues and eigenvectors and their importance in principal component analysis. So that being said, that's all what we covered. So if you're interested in looking at this, be sure to check out the full video that's posted on Cohere's YouTube channel. And also feel free to contact me and look at my YouTube channel for any further questions, or if you have inquiries or want to dive deeper into any of these topics. So yeah, let's begin. So the first question that I got was looking at the derivative lens. Someone asked, how are derivatives applicable to classical machine learning algorithms such as clustering and decision trees, etc.? So we talked about how derivatives and gradients are used in like the gradient descent type algorithms that are used often in backpropagation and neural networks. But what about these other traditional machine learning algorithms? So we're going to dive into each one of these separately, and I'll show you whether derivatives are applicable in these settings or not. So first of all, if we look at the k-means algorithm, there we go. Let's look at their gradient use. So k-means is an optimization algorithm, and even though it doesn't explicitly compute derivatives, so it's still optimization. So there was a lot of questions where, okay, you have optimization even if it doesn't explicitly compute derivatives. So this is a case where it is an optimization algorithm even though it doesn't explicitly compute derivatives. So if we look at its objective function, this algorithm actually minimizes the sum of square distances from each point to its cluster center. So while the k-means algorithm uses iterative reassignment and centroid recomputation instead of true gradient descent, the optimization it performs is analogous to a gradient-based method. Okay, so that's just important to understand there. And in Gaussian mixture models, known as GMMs, a clustering algorithm based on probability expectation maximization is used, which is derived using calculus and optimization theory, but still doesn't require you to compute derivatives directly in your practice. So this one just kind of shows how it's like analogous to a gradient-based method, even though it's not actually a gradient-based method. And for further clarification, gradient-based method is a derivatives method because, just to repeat, a gradient is a collection of partial derivatives. Looking at our next one is decision trees. So there's no direct derivative use in decision trees. Some decision trees example are CART or ID3, and decision trees built trees using rules based on metrics like Gini impurity, entropy, or information gain. So these metrics are calculated combinatorially or using logarithms, not through calculus or derivatives. So decision trees themselves have no direct derivative use. However, there's indirect use in ensemble methods. So this is kind of important to open your mind to how maybe not directly for decision trees we use derivatives, but we often use decision trees in ensemble methods and ensemble algorithms. So for example, in gradient boosted trees like XGBoost or LightGBM, gradients of a loss function are used to fit new trees to the negative gradients or residual areas of the previous trees. So here derivatives are explicitly used to update the model in an additive way, making gradient boosting a bridge between classical and gradient-based machine learning. Okay, so here we can show that indirectly, if we use ensemble methods, we still need to use those gradients over there, okay, because we're using them to fit the new trees to the negative gradients. So again, gradients, very important to know. Even if we don't use them everywhere, there's a lot of indirect cases. So please just learn them, write them down. And if you have any questions, let me know. Next, support vector machine or SVM. This is another classical or traditional machine learning algorithm. So SVMs involve solving a convex optimization problem where derivatives are used to find the optimal separating hyperplane. So the optimization uses Lagrangian duality and requires taking derivatives of the loss function and the constraints. So again, support vector machines, definitely need to know your derivatives for these ones. And lastly, we're going to look at the naive Bayes. So no derivatives are used for this algorithm. It's a probabilistic model based on Bayes' theorem with strong independence assumptions. So it involves computing probabilities, not gradients, and hence it does not use derivatives. So this one is really kind of hints that you should dive into probability and statistics a little bit more. Just for your reference, I do have a video out on Bayes' theorem and actually how to derive Bayes' theorem from scratch, and I discuss the importance of independence and the other conditions required. So be sure to check out that video if you want to learn more on the probability side. So just in general, like in machine learning, like you have so much calculus and linear algebra behind it with all like the derivatives and eigenvalues and vectors. But on the other side, machine learning and data science is very probability and statistics heavy. So a lot of algorithms in these processes will require a strong fundamental of probability and statistics. So I recommend that you definitely brush up on that if you're going forward with machine learning. So here I just put a little bit of a summary table to help us kind of understand these main classical algorithms. So if we go through again, K means clustering. Does it use derivatives? Not directly, but it has some, optimization is conceptually linked to gradient methods. GMM clustering indirectly uses derivatives for the EM algorithm. So the optimization framework is derived via calculus. Decision trees, straight up, do not use derivatives. They're based on discrete splitting criteria, like we mentioned. However, gradient boosted trees do use derivatives. They use gradients to update their trees. Support vector machines, yes, they absolutely use derivatives. They use convex optimization, uses gradients. And finally, naive Bayes, like we just discussed, does not use derivatives. It's probabilistic and based on counts and Bayes' rule. So that kind of sums up our first question. I had a lot of people asking different variations of this type of question. So it kind of asks, when are derivatives, partial derivatives, gradients used for classical machine learning problems? So gradient descent algorithm, 100% uses derivatives all the time. This one's huge for neural networks, large language models. But then we also have a couple of these other more traditional and classic algorithms. So now you know when derivatives are applicable or not. Let's dive into the next question. So the next question asks, when can we use cosine similarity and when can we use Euclidean distance? So this was on our linear algebra side of the session where we're starting to look at these distance metrics. And just for context, we use these distance metrics to compare vectors in an embedding space, in a latent space. We in language models, we convert our natural language we encode it into these embeddings, which are these vectors that can be multidimensional. I've worked with vectors that are over 1,000 dimensions, and the whole process is that we want to figure out what is the relationship between these vectors? How similar are they to each other? In language models, the more similar a vector is to each other, then we automatically assume that it has more semantic or stylistic similarity in terms of the content that vector represents. So this is often a question that I've heard a lot, that when do we use different types of distance metrics? So just caveat, there are multiple different types of distance metrics. Just in my, experience, these are the two that I've seen come up most frequently. So let's dive into this. So cosine similarity and Euclidean distance are both ways to measure how similar or different two vectors are. But they capture different kinds of relationships, and the choice between them depends on what matters most in your data. Do you care more about the magnitude or the direction? So we're going to dive into both cosine similarity and Euclidean distance in greater detail so you can now make informed decisions of when you want to use both. And just so you know, I've done research projects where for part of my research, I'm using cosine similarity because that makes the most sense. And for other parts of my analysis, I'm choosing to use Euclidean distance because that makes more sense for that point in research. So just know that you can use both of them within a same project. So cosine similarity. So it measures the angle between two vectors, so i.e. their direction. So the answer of cosine similarity, or the output, is between -1 and 1 inclusive. So if you get a value of 1, it means that your vectors are in the exact same direction. If you have a result of 0, that means your vectors are orthogonal, meaning they're perpendicular or 90 degrees to each other. And that means that your vectors are completely unrelated. And then lastly, a score of -1 indicates that your vectors are in opposite directions. So for reference, cosine similarity is based off of the normalized version of dot product, which you can see in our formula below. We have that cosine similarity between two vectors a and b equals the dot product between a dot b divided by the magnitude of a times the magnitude of vector b. Okay, so in my session earlier, I discussed dot product, and dot product, one of the formulas is the magnitude of a times the magnitude of b multiplied by the cosine of the angle between the two vectors. And we know that cosine of 90 degrees, or cosine of pi over 2, equals to 0, based off of the cosine graph. So that's why if we get an output of 0, that means that the vectors are 90 degrees to each other. They're orthogonal, and that's innate from the properties of the cosine function. Okay, so now that you know that, when do we use it? So we use cosine similarity when we care about orientation, not magnitude. So for example, your data is high dimensional and sparse. You might use it for text data in natural language processing. Additionally, the scale of your features doesn't matter. And lastly, maybe you're comparing document embeddings, user preferences, or semantic similarities. Semantic similarities is a huge one. That's where I often use cosine similarity. And here are some example use cases. You can do recommender systems, for example, similar users or items, document similarity in NLP, the TF-IDF vectors, and lastly, clustering word embeddings. So definitely add cosine similarity to your toolkit for measuring similarities between vectors. Let's look at Euclidean distance now. So Euclidean distance is what you think of like normal distance in terms of your everyday life. You walking to school, the distance between, I don't know, your neighbor's house to your house, it measures the straight line distance between 2 points. So the Euclidean distance is the square root of the sum of a minus b all squared. Okay, so this is also very similar to Pythagoras' theorem. This is pretty much the same formula, where you take the square root of the first vector squared times the second component, basically. So you're looking within each component, finding the difference and squaring it. So this is a common formula that we often use. Just so you know, again, there are many different magnitude formulas out there. Euclidean distance is analogous to the 2 norm. So just keep in mind that there are many other ways, but this is a very common method. And again, it's just measuring that straight line between 2 points. So when would you use Euclidean distance? So you use it when you care about the actual magnitude or the physical proximity between 2 vectors, 2 items. Often you use it when your data is in low to moderate dimensions. All features are similar scales, or if they're not, then you would have to normalize them. And then you use it when you want to preserve geometric structure, when you want to find that actual distance in space. Think about you and your neighbor's home. You want to find the actual distance between the 2 houses. Are they 5 meters apart? Are they 20 meters apart? We want to find that actual physical proximity. In terms of machine learning algorithms, what are some example use cases? We can use them in K nearest neighbors, KNN, which is classification or regression. K means clustering. The default for this one, it uses Euclidean distance, though you can always change it if you want. Oftentimes it's used in computer vision, in image similarity, and distance-based anomaly detection. And that's it. So I really hope that you enjoyed this Q&A session today. I just wanted to work on kind of addressing the most frequently asked questions that I got after our session. Again, if you have any further questions, please definitely comment on this video. I will be sure to answer it. Subscribe to my channel. Also subscribe to Cohere's channel. We have so many great videos coming out for you all the time. And please stay involved with the machine learning math community at CohereLabs. It's such a wonderful space for researchers around the whole world to connect with each other and tackle mathematical problems together and really dive into understanding the fundamentals of mathematics and how it relates to core machine learning, deep learning, and large language model principles. I'll be there every 2 weeks. I teach a lecture. Our next one is July 14th, 11 a.m. EST, so watch the events for that. Again, we're in 2025 right now. And yeah, please feel free to reach out to me if you have any questions, and definitely join our community. We look forward to hearing from you, and we'll see you next time.